Dr. Lamb, this is the first time you get to hear my voice. Well, I'm going to run you through a demonstration of the Scientific Methods Lab. You should have out your lab manual if you have it, or have downloaded the file from D2L. It will be up there. Do that right now if you haven't done so already. All right? Pause not you, the students. I'm speaking to the paraprofessional who's filming me. Pause the video right now if you haven't done that. Download the form or get out your lab manual and then follow along. Okay, are you back? Okay, good. So we're testing this, giving a demonstration of the scientific method. We're going to test a hypothesis. A hypothesis is an educated guess, a preliminary answer to a question that can be disproven. And we're going to find a hypothesis. We have a hypothesis to work on, and we're going to put it in a situation where it can be proven wrong, or it can be supported by the evidence. We're not going to prove it. You don't prove hypotheses. Science is not logic, and it's not, philosophy. You don't prove things. It's not math. So the hypothesis is going to step. Again, you're going to state a hypothesis. We're going to make a prediction based on that hypothesis. We're going to test that hypothesis. In this case, we're going to run an experiment. There are other ways to do this. We're going to collect data. We're going to analyze the data. I'm going to see if indeed the data supports the hypothesis. In other words, if our prediction came true, or if it refutes the hypothesis, which means our prediction did not. So what's the problem? The problem has to do with the energy of an object in motion. It's called kinetic energy. And this is something that Isaac Newton came up with. Now, Isaac Newton came up with a formula for the energy of motion, or kinetic energy, saying that the energy of motion is 1/2 times the mass, which is how much these balls weigh, times the velocity, how fast it's moving along with the direction, squared. So based on that, we're going to the question we're asking is, which is more important? Which creates more energy of motion in a moving object? The mass or the velocity? Now, those of you who know how to make a math problem work have probably figured out the answer. But I'll give you before I confirm it for you, I'm going to do a little thought experiment. I'm going to plug some numbers into that equation, that 1/2 times mass times velocity squared. So let's start off with mass of velocity equal to 1. So in that equation, it becomes 1/2 times 1 times 1 times 1 again. That's what 1 squared means. All those 1's multiplied together just equal 1. So it becomes 1/2 times 1, or 1/2. Right? That's the starting, the null hypothesis. That's where we start. So for comparison, I'm going to double first the mass and then the velocity. So let's plug in the mass. We double the mass, and mass is now 2. So the equation becomes 1/2 times 2 times 1 times 1. All those 1's together equal just 1, so it becomes 1 times 2 times 1/2, or 1. Double the mass, double the energy. Remember, the starting energy was 1/2. That's pretty intuitive. Now, listen to what happens when I double the velocity. It becomes 1/2 times 1 times 2 times 2. 2 times 2 is 4, which means this whole equation becomes 1/2 times 4, or 2. Double the velocity and you quadruple the energy. So based on what we know already, this is what makes this an educated guess. Velocity should be more important in the energy of a moving object. In this case, a falling ball that I'm going to drop into this cat litter. Right? And I'm going to go test that for you. Okay? So it's pretty, first off, let's look at the difference in in mass. This is about a 4 times more massive ball. 4 or 5 times more massive ball. No, it's more than that. Much more massive ball than this one. So the crater should be big. So we're going to drop both these balls from the same height. They'll be moving at the same velocity because they're both being accelerated by gravity. And watch what happens to the craters. The bigger ball makes the bigger crater. Now that's not a surprise. Oh no. It's not for you. But watch what happens with the same ball, dropped from different heights, which means it'll be moving at different velocities. If I drop it from a higher height, it'll be moving, if I drop it from twice the height, it'll be moving at twice the velocity. So I'm going to drop it about here. Okay, and that's how big it is, and I'll try and disturb the crater as little as possible. And I'll drop it from in here, about twice as high. Well, that doesn't look very promising, but that ball buried itself much deeper, and I want to show you something. This is how you do it, by the way, if you're actually in class. Lay that ruler across here. Find, here we go. This is the metric side in centimeters. And measure how deep it is. Just far enough down. Now, if you excuse me, I'm going to have to go, you know, see my back as I go look at this. I should have planned this out a little bit better. Right. Ugh. That's about 2.3 centimeters deep, about 23 millimeters. And it is 6.5 millimeters, 6.5 centimeters across, or 65 millimeters. This one over here